Hello, and welcome to the 7th module in our series on petroleum production engineering. Our objective in this module is to learn how individual well and field performance trends may be analyzed so as to provide information about future producing rates of oil, gas, and water, cumulative production, and most importantly, the remaining oil and gas reserves. Let's begin by listing the 4 standard methods recommended by the Society of Petroleum Engineers for estimating reserves. They appear in a publication entitled Standards Pertaining to the Estimating and Auditing of Oil and Gas Reserves Information, which was approved by the SPE Board of Directors on October 30th, 1979. Under Article 5, Section 3, we read, the acceptable methods for estimating crude reserves include, first, the volumetric method. Second, evaluation of performance history, which evaluation may include an analysis and projection of producing ranges, reservoir pressures, oil-water ratios, gas-oil ratios, and gas-liquid ratios. Third, development of a mathematical model through consideration of material balance and computer simulation techniques. And fourth, analogy to other reservoirs, if geographic location, formation characteristics, or similar factors render such an analogy appropriate. It is the second of these methods, the one based on evaluation of performance history, which is of interest to us here. With reference to this specific procedure, we read further, for reservoirs with respect to which performance has disclosed reliable production trends, crude reserves may be estimated by analysis of performance histories and projections of such trends. These estimates may be primarily predicated on an analysis of rates of decline in production and on appropriate considerations of other performance parameters, such as reservoir pressures, oil-water ratios, gas-oil ratios, and gas-liquid ratios. For the purposes of this method, then, it is assumed that the factors which influence the performance trend of the well or field in the past will continue to govern its future performance in a similar manner. In other words, without information to the contrary, we assume that what has occurred will continue to occur. It is this assumption which allows us to extrapolate future trends from past performance.
Decline curves are the cornerstone of this method, and are so named because of the tendency of the well's production to decline over time as the reservoir is depleted or as fluids must travel greater distances through the formation to reach the well bore. The rate of decline depends on many factors, including the reservoir drive mechanism, pressure, and rock and fluid properties. There are a number of ways in which production decline data can be shown graphically. Here we see the production rate, Q, plotted against time. The rate is constant during the well's early life, when either proration or maximum efficient rate limits were placed on it. Thereafter, the rate begins to decline. Here we see the production rate plotted against the cumulative production, N sub P. The profiles of the two curves are somewhat similar, with the production rate declining as more fluids are produced from the reservoir. We will often plot the percentage of oil or water cut versus cumulative productions in situations where the ultimate production rate is controlled by the amount of water production we can handle on the lease. Here we have plotted the percent oil produced. When the value of the oil produced becomes equal to the cost of disposing of the water produced, we have reached the point of abandonment. In bottom water drive fields, we might plot the location of the oil-water contact in the formation against cumulative production. When the contact reaches the top of the sand, we know that we have recovered the crude reserves for this well. In a similar manner, we might plot G sub P, the cumulative gas produced, versus the cumulative oil produced. This plot is particularly useful in cases where we know the expected total of gas to be produced. This is used as the abandonment point for the well. One of the more important plots for estimating reserves is that of the average reservoir pressure, P sub R, bar, versus time. Either pressure buildup tests or observation well data are used for this plot. Finally, we should remember that for fixed volume gas reservoirs, the average reservoir pressure over Z, the compressibility term, will plot as a declining straight line function of the cumulative gas produced on linear coordinate paper.
Not all of the preceding curves declined. However, they are often collectively referred to as decline curves. The most important of these curves involves production rate declines, and we shall devote a major portion of this module to their characterization.
Production rate is by far the most popular dependent variable used in projecting future performance. It has the advantage of being readily available and easily recorded. When no major changes in operating procedures are made and no stimulation treatments are applied, the rate curves normally show a fairly smooth declining trend over extended periods. This trend lends itself to extrapolation. This smoothness of decline is one important requirement for extrapolation. A second requirement is that there be a known endpoint. That is, a production rate at which a well or field begins to lose money if production continues. This point is referred to as the economic limit production rate. If we incorporate this value into our rate versus time and rate versus cumulative production curves, we can extrapolate each trend line to this cutoff point and thereby determine, for the first curve, the number of years the well or field will produce profitably prior to abandonment, and for the second curve, the cumulative production at the time of abandonment. The endpoint may also be a minimum oil cut. In this case, we use the oil cut versus cumulative production curve in order to calculate the total production at the time of abandonment. Likewise, if the known endpoint is the movement of the oil-water contact to the top of the oil sand, then we would use a plot of the oil-water contact elevation versus cumulative production to find the total production prior to abandonment. If the total expected gas production has been calculated with a degree of accuracy and serves as our cutoff point, we would plot the cumulative gas production versus the cumulative oil production in order to find the total oil to be produced. Finally, we should add that for a gas well, the minimum producing rate is determined by the back pressure imposed on the well, with or without compression. When the value of this limiting back pressure is converted to a value of average reservoir pressure divided by Z and plotted on the pressure versus cumulative production curve, the quantity of ultimate producible gas reserves is obtained.
But a word of caution. There are two important limitations on our projections. First, the total reserves estimated to be produced must be reasonable. And second, the total time during which those reserves are to be produced must also be reasonable. If the projected total reserves greatly exceed the volumetric estimates, then we have made an error in our calculations. We may be producing from a much larger drainage area than the drainage area of normal spacing. If this is the case, it won't be long before an offset well is drilled, thereby diminishing the reserve estimates and shortening the life of the well. Now, let's spend a few minutes learning how decline rates may be expressed mathematically, and also learn which graph paper is best suited for plotting them. The three types of decline curves most commonly used are the constant percentage or exponential decline, the hyperbolic decline, and the harmonic decline. Let's look at the mathematical characteristics of each.
With constant percentage decline, the change in production rate per unit of time is a constant function of the production rate Q. This means that the decline rate, capital D, is constant, and a negative sign is added to the right side of the equation so that D will have a positive value. If the variables of this relationship are separated, and integration takes place between the appropriate limits of flow rate and time, we obtain the rate-time relationship for the constant percentage decline curve. This equation states that the flow rate Q at any time t is equal to the initial flow rate prior to the beginning of decline, multiplied by e to the negative decline rate d, multiplied by the time during which the decline occurs. This is the rate-time relationship for the constant percentage decline curve. If we wish to obtain the rate cumulative production relationship, then we must integrate the flow rate, Q sub t, over the time period t. This integration gives us an expression for N sub p, which is equal to the initial production rate, Q sub I, minus the final production rate, Q sub t, the production rate at abandonment, divided by the percentage decline rate, d. Note that d is a fraction and not a percent. This is the rate cumulative production equation for the constant percentage decline curve. For constant percentage decline, the decline rate is constant. We can state that d is equal to k. For the next two decline curves, the decline rate is not constant. Let's look now at the other two decline curves. For hyperbolic decline, the decline rate is proportional to a fractional power of q. We may express this by saying that d is equal to k times q to the power n. N lies between 0 and 1. For harmonic decline, the decline rate is proportional to q. We express this by saying that d is equal to k multiplied by q. We see then that the harmonic decline and constant percentage decline are special cases of the hyperbolic decline. That is, n is equal to 1 for harmonic decline and 0 for constant percentage decline.
On a more practical basis, we note that for both hyperbolic and harmonic decline curves, the decline rate will be high at high production rates and low at low production rates. Let's now see what happens when we take the expressions for each of these last two curves and integrate them.
We start with the hyperbolic decline curve. Beginning with our decline rate definition, we see that d, the decline rate, is a function of the flow rate q and the exponent n. Integrating this relationship between the appropriate limits of time and flow rate, we obtain the rate-time relationship. Here we see that the flow rate q at any given time, t, is equal to the initial flow rate prior to the beginning of decline, q sub I, multiplied by the term 1 plus n, multiplied by d sub I, the decline rate at the initial flow rate, multiplied by t, the time at which the flow rate is being calculated, all raised to the minus 1 over n power. We note that in order to calculate a flow rate q at any time t, we must know the value for n, and have calculated a value for d sub I. We shall show how this is done shortly. With one more integration, we may calculate the rate cumulative production relationship. The integration is that of q sub t with respect to time over which production takes place. In this manner, we obtain the values for capital N sub p in terms of the initial production rate, q sub I, the production rate, q sub t, at the point in time when we wish to know the cumulative production, and two constants, small n and d sub I. With these various values, it is an easy task to calculate the cumulative production, N sub p.
Now that we know the basic mathematical relationships for both the constant percentage and the hyperbolic decline curves, let's take just a few more minutes to develop the relationships for the harmonic decline curve.
We begin once again with our decline rate relationship. In this case, one where d is equal to k multiplied by q raised to the first power. With separation of variables and integration between the limits of time and flow rate, we are able to calculate the rate-time relationship. In this case, we see that the constant n no longer appears. We also see that we must know both the initial flow rate, q sub I, and the decline rate at the initial flow rate, d sub I, in order to calculate the flow rate q at any given time, t. Once again, if we integrate the flow rate q sub t with respect to time and flow rate, we obtain the rate cumulative production relationship shown here. We note that the cumulative production N sub p at any point in time, t, is equal to the initial flow rate q sub I divided by the initial decline rate, d sub I, multiplied by the natural log of the ratio of the initial production rate to the production rate at time t.
It becomes clear that our calculation procedures are sequential. That is, that we must first calculate the decline rate, d, and in the case of hyperbolic decline, a value for n. With these values, we use the rate-time relationship to calculate q sub t, and then, knowing a value for q sub t, we go to the rate-cumulative production relationship to calculate a value for n sub p. With these relationships, then, we can calculate the flow rate and cumulative production at any given time. Before proceeding to see what type of curves these relationships give us, let's take a few minutes to be sure you understand what has just been presented. Work problems 7.1, 7.2, and 7.3 in your workbook. Now that we have developed the mathematical relationships which apply to our three types of decline curves, let's see how each of these curves plots on various types of graph paper. The two types of relationships we will be plotting are the rate time and rate cumulative production curves, and we will see how they plot on three different types of coordinate paper: linear, semi-log, and log-log. We shall plot three curves on each, one for the constant percentage decline, which we shall label with Roman numeral 1, one for the hyperbolic decline, labeled with Roman numeral 2, and one for the harmonic decline, labeled with Roman numeral 3. In order to obtain these curves, we must assume specific values for n and d. For curve 1, n is equal to 0, and d is equal to 0.03. For curve 2, n is equal to 1/2, and d sub I is equal to 0.10. For curve 3, n is equal to 1, and d sub I is equal to 0.3. Now let's see some examples.
We see that the production rate decreases with both time and cumulative production. We also note that the decline rate is greater for curve 3 than for curve 2, and curve 2 in turn declines more rapidly than curve 1. We also note that as a result of the more rapid decline rate, curve 3 reflects the least cumulative production. Curve 2 reflects a higher cumulative production, and curve 1 reflects the highest cumulative production of them all. The differences in cumulative production are rather substantial. The most important observation is that curve 1, the constant percentage decline curve, is a straight line when rate is plotted versus cumulative production. It is for this reason that this specific decline curve is so popular. Note that the decline rate d is equal to -1 times the change in flow rate divided by the change in cumulative production. This, in turn, is equal to -1 times the tangent to the straight line. This observation provides a graphical technique for calculating d. If we now redraw the same curves on semi-log paper, with the rate axis converted to a log scale, we see once again that the curves tend to be located in the same place relative to each other. This is as it should be. But now we make a second important observation. We note that the rate time curve 1, the constant percentage decline curve, is a straight line on semi-log paper. This further reinforces our understanding as to why the constant percentage decline curve is so popular. The rate time curve is a straight line on semi-log paper, and the rate cumulative production curve is a straight line on linear paper. The fact that they are straight lines allows for easy extrapolation. Notice that curve 3, the harmonic decline curve, is a straight line on semi-log paper. With the straight line plot and a knowledge of the initial production rate, we can calculate the initial decline rate, d sub I. We also note that on the rate time plot, a value for the decline rate d in curve 1 can be obtained graphically by calculating the tangent to the slope and multiplying that by -1. This graphical estimation for d can be compared with that calculated on the rate cumulative production curve on linear paper. Once more, let's plot the same curves, but this time on log-log paper. We see the results here. Note that the curves have shifted to the upper right-hand portion of the diagrams, and that none of the curves is a straight line. In the case of the hyperbolic decline curve, curve 2, the rate-time relationship as well as the rate cumulative production relationship can be straightened using appropriate shifting procedures so that they become straight lines on log-log paper. In addition to the extra work involved in shifting, this type of paper has the further disadvantage of crowding the horizontal scale at the point where the answer is sought. For this reason, special graph paper for hyperbolic decline has been developed, making it possible to obtain straight lines when plotting rate versus time and rate versus cumulative production.
The next question we must ask is which of the three types of decline curves should be used to represent the decline performance of our wells or fields? There are a number of published studies which will assist us. In 1924, Cutler undertook an intensive investigation of a large number of oil field decline curves and found that constant percentage decline curves were in good agreement with production data during early years of production, but often gave results that were too conservative during the later stages of production. He expressed a preference then for the hyperbolic decline curves. Nemoto compared the use of both the constant percentage decline and hyperbolic decline for a number of Japanese oil fields and arrived at an opposite conclusion. That is, that the constant percentage decline curve was preferable. Shea, Higgins, and Lechtenberg in 1964 reported on their review of 347 California reservoirs. In cases where they could take a 5-year production history, extrapolate the decline curve for an additional 5 years, and then compare the prediction with what actually took place, they found that the constant percentage decline curve was most accurate. In 1968, Ramsey, in his master's degree thesis at the University of Tulsa, reported his findings on the analysis of field data. He reviewed production data for about 1,150 leases and 250 pools in 7 different states in the United States. Using the same criteria as Shea, that is, using decline curves to predict production 5 years into the future, and then comparing those predictions with what actually took place, he found that the constant percentage decline curve gave the best results. From these studies, you will realize that there is room for disagreement among the investigators, especially since the data they analyzed were different. As a practical matter, and as a matter of convenience, semi-log paper is most often used for production rate versus time extrapolations, while linear coordinate paper is generally favored for production rate versus cumulative production extrapolations. The use of straight line extrapolations for both means that a constant percentage decline is being assumed. This generally results in conservative estimations, especially during the later life of a well or field.
We see here that a semi-log plot of rate versus time will give an abandonment prediction at time T1, whereas the hyperbolic decline curve would give an abandonment time at T2. Later abandonment time, of course, means that the well will ultimately produce a greater volume of reserves. Experienced engineers will usually allow for the fact that the constant percentage decline rate will be conservative and compensate for this by graphically flattening the decline slope in the later stages of production.
We now realize that the constant percentage decline curve has the broadest application in practice. This means that during the well's decline period, we can plot the production rate versus time as a straight line on semi-log paper, and production rate versus cumulative production as a straight line on linear coordinate paper. We also know that we may wish to stretch the curves outward a little in their later years of production. The only limitation to the use of constant percentage decline curves seems to be for tight, less permeable reservoirs. For these reservoirs, a semi-log plot of production rate versus time initially follows a hyperbolic decline and then flattens to a constant percentage decline when the transient reaches the radius of drainage. Except for tight reservoirs, then, the constant percentage decline curves are to be preferred. Now, let's take a few minutes to learn a little more about these two specific curves and the way in which the equations which represent them may be used to calculate specific information for the well or pool. Then we shall see how they are used with actual data.
You will remember that the production rate versus time and the production rate versus cumulative production relationships are given by these two expressions. D is referred to as the continuous decline rate and has the dimensions of 1 over time. The units for D and those for T must be the same. Likewise, the production rate should be given in the same time dimensions. In other words, if the production rate is in barrels per month, T should be in months and D in units of 1 over months. Let's use these equations to solve the following sample problem. We are given that the initial production rate at the onset of decline is 6,000 barrels per month. A plot of the early production history indicates that the decline constant D is equal to 0.025 and has units of 1 over month. We have calculated that the economic limit production rate for the well is 75 barrels per month. We are asked to calculate the production rate after 3 years of decline, the total reserves, and the time to abandonment. We may calculate the production rate after 3 years of decline by solving our rate-time equation with T equal to 36 months. The production rate at that time is found to be 2,439 barrels per month. In solving the second part of the problem, that is the total reserves, we use the rate cumulative production equation and the given data to yield a total producible reserves of 237,000 barrels. In order to calculate the time in months to abandonment, we use our production rate versus time equation, the economic limit production rate, and the decline rate D. We solve then for T and find a value of 175 months or 14.6 years. We should check these values against our volumetric estimates, and quite likely we would find them to be reasonable. We are often asked to quote a well's decline rate on an annual rather than a daily or monthly basis. This can be done if we make several observations about our rate-time equation. We will begin by assuming that our time, T, is in years, and our constant, D, is in units of 1 over years. Units for production rate for this equation alone may be given in barrels per day or barrels per month, provided the units for time in the exponent are the same. The consistency of units must be maintained in the exponent. With our basic equation, it can be shown that the ratio of production in subsequent years, that is, the production rate on the first day of the second year divided by the production rate on the first day of the first year, is equal to the ratio of the production on the first day of the third year divided by the production rate on the first day of the second year, and so forth. This ratio is equal to E to the minus D, and is a constant, telling us that the ratio of the production rates in successive years is always a constant. This ratio is often written as being equal to 1 minus small d.
Small d is often referred to as the annual production decline rate, and should be distinguished from capital D, which is the continuous decline rate. Let's use this information to solve the following problem. We're given that the production rate on the first day of year 1 is 1,000 barrels per day, and on the first day of year 2, it is 750 barrels per day. The ratio of these two production rates is equal to 1 minus small d. The value of d is then found to be equal to 0.25, or an annual production decline rate of 25%.
It can be shown that the monthly decline rate D sub m is related to the annual decline rate D by the expression shown here. An annual decline rate of 25% works out to a monthly decline rate of 2.35%. As you can see, the calculations are quite direct. An annual decline rate D equal to 25% is equivalent to a continuous decline rate, capital D, of 0.2876 per year. And if we divide that by 12, we get 0.02397 per month. Each of these has its respective percentage values. Often you will hear the continuous decline rate, capital D, referred to as the nominal rate, and the annual decline rate, small d, referred to as the effective decline rate. The former is what occurs continuously on a smooth curve. The latter is based on values of production at discrete points in time, for example, from the first year to the second year. Since production is usually reported on a discrete basis, that is, daily or monthly, we often make use of the effective as opposed to the nominal decline rate.
Jan Arps, for example, prepared a series of tables for constant percentage decline curves showing the production rate and cumulative production over time for a series of effective decline rates.
Here we see a table of production rate, cumulative production, and time for an effective decline rate of 1 3/4% per month. Tabular data is normalized to the initial production rate. This means that the tabulated values must be multiplied by the initial production rate. For example, if the initial production rate is 10,000 barrels per month, we would enter the table at the 12th month and multiply each value by 10,000. This would give us a production rate in the 12th month of 8,090 barrels per month and a cumulative production of 107,188 barrels during the first year. A number of these tables appear in your workbook, where they're available for easy reference. One definition that we should provide you with before continuing is that of the loss ratio. It is defined as the inverse of the nominal decline rate, or as we see here, is equal to Q divided by dQ over dt. The loss ratio is often applied to tabulated production data to see how the ratio trends with time. For constant percentage or exponential decline, the loss ratio is constant.
Now would be a good time to make sure you understand the material just covered. Stop the player and work problems 7.4, 7.5, and 7.6. We're now ready to discuss the use of production data. Before doing so, though, we should give you some idea as to how data are collected, recorded, and made available to the user. Your company very likely has its own computer database system. In order to show you the scope of one such system, let's visit Dwight's Energy Data in Dallas and speak with Ron Samuels, its president.
Here at Dwight's Energy Data, we monitor production data from 19 states in the Gulf of Mexico and offshore California. In doing this, we keep track of over 528,000 properties. These properties are made up of gas wells and oil leases. The total number of wells that are incorporated into our system would exceed 1 million properties. One of the unique things in what we do is keep track of the data from the states, in that each state has data reported to it in different forms. Some states actually get data from operators, others from gathering pipelines, gas pipelines. Here at Dwight's, we take all of the data that's turned into the different states and put it into a common format. Doing this, there's about a 4 or 5 step procedure that takes place. Initially, when the data is turned into the states, the state will then take the information and do one of 2 things with it normally. They will take it into their own internal data processing system, or else file the data for public record. Those states that have computerized databases, we purchase the data from the state and convert it to our standard formats. Those states that do not have computerized production statistics, we go in and microfilm the information, bring it back to our office, and take it through a clerical process, which we will show you. This clerical process involves one of 2 things, either taking the information and posting it to ledger books and then key punching the information, or in the case of some states, it is possible to key punch directly from the microfilm data. After this is done, it is then taken into our master files and put into a standard format. This is the one real advantage that the end user sees, is they don't have to deal with the 19 different states in separate formats. All the data will be collected and assimilated into one common format. Then from that point, after the data is into our master files, we generate information in microfiche, which we will show you, online computer services, hard copy, and in fact people can purchase the entire magnetic tape system. Back here at Dwight's, this is one of the first steps in the gathering of the statistics that takes place. We have received microfilm that we are now going to post the production statistics into ledger books. This is done to enable us to key the data using a common serial number. Once the information has been posted and the clerk has done some initial checks to the data, it is then taken to our key punch department where it is put onto magnetic tape. The second step at Dwight's involving the production statistics is the key punching of the information that has been posted by the clerks into the ledger books. Once this data is brought to the key punch department, job slips are made and the data is key punched and verified. The ledger books is just one of many steps that we key punch from. Other information that we use is key punched from microfilm, and the microfilm that is brought directly into Dwight's as filmed at the state agencies. Key punching the information that is turned into the regulatory agency is accomplished on those documents that have control numbers. These control numbers and the production is key punched directly to magnetic disc, which we later put to magnetic tape. Once all the information has been verified from either the ledger books or from the microfilm, we take the information from magnetic disc and put it to magnetic tape. The magnetic tape is then taken into our main computer room, at which point all of the state master files are updated and put into a common format. This common format is then used to generate the output reports that are used by the clients. Here in the central processing room, this is step 3 in compiling the production statistics. The magnetic tape that comes from the key punch department and or the different state agencies are brought into this room and updated into a consistent format. We have over 7 billion characters of online statistics. We also have approximately 5,000 reels of magnetic tape. The gas test, the gas monthly production, the oil monthly production, and other related data are all compiled here and put out into 4 different formats that we make available to our customers. There are 4 basic types of information that you can get. You can get hard copy reports, microfiche reports, online reports, and in fact you can buy the entire system on magnetic tape. This is available by Railroad Commission District, by state, or for the entire file. Here at Dwight's, after we come from the central processing room, we generate a print tape. These print tapes are taken into the computer room where they are printed on laser printers and impact printers. We do this every 3 months for our clients. We in fact generate only those tapes that are needed and only the number of reports that are needed each 3 months. This is an example of the type of report that we produce. This particular sample is for a gas well. All the pertinent information concerning the property is shown. The state, the field, the operator, the well name, well number, the reservoir it produces from, the total depth, perforated intervals, gas and liquid gravities, when the well was completed, when it first started, and its initial production. We then take the statistical data and show the production in 6-month increments for the last 8 years with annual totals, cumulative totals, and cums to test date. The actual test dates are displayed with potentials, wellhead pressures, bottom hole pressures over Z. We then take the tabular data and plot the information. We have 2 horizontal and 2 vertical scales. The first scale pertains to the pressure information. The Z represents bottom hole pressure over Z. The 0 represents wellhead shut-in pressure. The initial pressure would appear on the far side of the scale at 0 cum. The cumulative information is displayed on the bottom scale so that you can take the wellhead information and each test from initial test to last test is plotted. Also on this particular gas plot, we have a rate cum decline curve. The rate cum scale comes from the other side of the page, plotting downward using an R symbol. The cumulative production is then displayed at the bottom scale. So this plot, in essence, has 3 types of plots on one page. a rate cume plot, bottom hole pressure over Z cume, and a wellhead shut-in pressure cume. This is one of several types of gas plots that are available. We also have rate time gas plots. In addition, we have rate time oil decline curves. Both of the last two are on semi-log paper and are available primarily on microfiche. One of the convenient ways to store gas and oil decline curve information is on microfiche. This spindle contains over 500,000 properties. We've been requested to look for a particular property which is in the Block 16 Devonian field in Texas and is called the Hill Unit. To accomplish this, you would find the appropriate report code for that area. In this case, it would be our report code 22. The microfiche then is indexed by field, operator, and lease name. And at the top of each field is the first field operator for that particular microfiche. You can then take the microfiche to either a microfiche reader or reader printer. Each microfiche has an index. In this case, the index is organized by field, operator, and lease name. You can find the appropriate grid location for the property of interest. In this case, the Hill Unit is located at grid H9. A pointer is available to go to that grid location, and once you have found the appropriate well, a copy can be made or an analysis can be done directly from the screen itself. To obtain a hard copy printout is accomplished by just pressing a button. This is one of many types of reader printers that are available on the market. The hard copy PZ rate cume decline curve can then be used for the analysis, be written on, filed into reports. The convenience of microfiche gives you the flexibility of generating just the hard copy reports for those wells you have interest in. The fourth and newest way to obtain production statistics from Dwight's is through our online database system. This database is on 2 worldwide networks. You can obtain information on properties that are contained in the Dwight's file anywhere in the United States and also through the worldwide time-sharing network. To look again once at the Hill Unit that we requested, we're going to go to our online system and have Fred Smith look up this well. Fred, if you would, let's run a TARS report and generate the output for the Hill Unit. What he will be doing, he will run a canned report. This report will ask for specific information. It will ask him to input a code sequence that is obtained from microfiche that we supply. This code sequence is the report code, county code, and identifier that we use for each property in the file. As he has input that data at this point, it is now searching off 580-some thousand properties for the particular well that we have requested. As you will see, this works quite rapidly as it has now found the property and is outputting the information. This information will be all of the production statistics, the header information, operator, well name, well number, total depth, perfs, as previously described in our hard copy format. There are a number of canned reports that are available to use, and also you have the opportunity to generate your own type of software. Where we will look at several types of data on this one report, test information, the actual monthly production and annual production. Then we'll be able to take this same data and apply it to a pen plotter. We will then plot the data on semi-log paper. And now we will begin the plotting routine that is taken directly from the online system. Both online companies have several plotters that you can use. This particular plotter is an 8-pin plotter, and we will be plotting a gas decline curve on a rate time basis. The plot, as you can see, generates the entire scale and the entire grid. This will be on semi-log paper. There's also a function where you can use pre-printed semi-log paper by inserting it into the plotter and bypass the drawing of the grid. These types of reports can be customized to the individual client's needs. There are several types of pre-formatted decline curves that are available, and then since you are tied directly to the online computer, you do have the flexibility to generate your own type of curve. You'll see the programs automatically calculate the horizontal and vertical scales based on the property that is being retrieved. This is now putting the rate. We'll then put the cumulative, or in this case it'll be the time scale. First plot you see here is the gas production for the Hill unit plotted on rate time. We will then plot the condensate production. It is now figuring the scale for the condensate barrels per month. The gas scale that was just plotted is on the left side, and the condensate is on the right side. The scales can both be easily recognized by the fact the scale that is printed in red will also be plotted in red. The scale that is in green is also plotted in green. Once the actual plot has been generated, then the descriptive data concerning the property is printed in the heading. This is very useful in doing overheads, individual property retrievals that have to be displayed for management. The data used in this format is used for reserve analysis by engineers, in exploration mode by geologists, also used by banking institutions in figuring loan values on particular properties. This type of data is available both for oil and gas for every property that is contained in the file, some 500,000 properties. And there are several types of scales that are available and several types of output reports. Some plot oil production, some will plot gas-oil ratios. You also have the flexibility to plot number of wells. In essence, the flexibility is to the user's discretion, and you can generate almost any type of plot necessary, even into pie charts, bar charts, and other type of graphs. This type of graph, however, is the most used.
These charts can be found in your workbook. Dwight's is only one of several companies that provide production data services. Your company very likely has its own, and we encourage you to look into its design and accessibility.